Hi everyone, today I'm going to solve a mechanical vibration problem in 8 methods. And from my perspective, each of these 8 methods are necessary to know and understand since each of them has its own advantages or disadvantages and it has its own kind of use. So these 8 methods are: 1. I'm going to find the analytical solution of the problem using dsolve command. Second, I'm going to find the numerical solution using ODE45. Since, as you probably know, not every equation has an analytical solution, so you must be familiar with numerical solutions. The third method is a transfer function approach. And transfer function approach has one disadvantage, and that is the initial conditions of the problem has to be equal to 0. This is a shortcoming of this method, but it is a powerful way to display equations and it has its own kind of use. So it is good to understand transfer functions. The fourth method, SSR approach, state space representation. It is so important for mechanical engineers and control engineers to be able to convert any differential equation into a state space representation. And the fifth method is solving the problem using Simulink. And the sixth and seventh methods are similar to the third and fourth method. So it is the same approach, transfer function and state space representation, but in Simulink instead of a MATLAB M file code. And the eighth method is using Simscape Mechanical module, which uses a drag and drop approach. So I'm going to start with defining the problem. So it is a mass damper system. So as you see here, there is no spring. And this mass is initially at rest and it is subject to an external force. Fa is the external force. It is a function of time. And this is the general form of its governing equation. So mx double dot plus cx dot is equal to the external force. And this external force is 10 newtons for 1 second. And after that, the force is going to be equal to 0. So I'm going to solve for 5 seconds. So time is from 0 to 5. For the first second, there is a constant external force equal to 10 newtons, and then the force is going to vanish. So I go to MATLAB and I create an M file named solutions. As always, I start with close all, clear CLC. First, I have to define constants. And I take M to be 0.5 kilograms. And I take the damping constant to be equal to 0.3 Newton second per meter. Now, method 1. It is analytical solution. You know, the analytical solution in one sense is the best solution since the result that you get from this method is exact. It has no errors. So if it is possible to find an analytical solution, you had better go for it. But the shortcoming of this method is that not every differential equation has an analytical solution. And in our example, since the external force is not continuous, it has a discontinuity at 1 second, I do not expect to find an analytical solution generally for this equation. But there is a trick that allows me to find an analytical solution, and that is I can decompose the function into 2 subfunctions. So as here, the function has been decomposed into 2 subfunctions, and in each of these subfunctions, the force is constant. So I'm going to do that. First, I type help dsolve to find the general form of the syntax of this command. And I have a separate tutorial on dsolve command. So if you're not familiar with analytical solution of differential equations, make sure you watch it first. So S is going to be the output of the solution, and it asks for the equation and initial conditions. So what is the equation? It is m times x double dot. So I have to define x here. So I type sims x of t. I define x as a function of t, and then I can define f to be equal to 10. So I write f1 and f2. So I have two separate equations. The first one is m times the second derivative of x plus c times the first derivative of x is equal to f1 actually. So it is equation 1. And equation 2 is the same equation, but the force is going to be equal to 0. Now I have to define the initial conditions, and as I said, the mass is initially at rest. So initially the position is equal to 0 and the velocity is also equal to 0. But I haven't defined velocity, so velocity is the first derivative of x. And this is going to be solution 1 for equation 1. Let me run it to see what happens. Okay, I got my answer, and if I plot S1 from 0 to 1, and I run it again, okay, it showed me an error. Okay, so it has to be condition 2, initial condition number 2. Now I run it again, and here I have my result for the first second. But for solving the equation from 1 second up until 5 seconds, I have to repeat these commands. Okay, so what are the initial conditions now? The position and velocity after 1 second has to be the new initial conditions. So in order to find that, here I have S1, and I have to find the value of S1 at 1 second. It gave me the results in a symbolic format, so I have to use double function to convert it into a number. So this is the final position after 1 second. So, and it is going to be the initial condition for the second part of the solution. And for finding the velocity, instead of S1, I define the first derivative of S1. So what does this line do? S1 was the position. It finds the first derivative of it with respect to time, which is going to be velocity. And using subs command, the number 1 is going to be fed into this function. So it gives me the velocity at time equal to 1 second. And this function only converts it into a double format. I have a separate video on MATLAB symbolic toolbox. So if this substitution is vague to you, you can go check that tutorial too from the top right corner. So I press enter, and this is going to be the velocity at 1 second. And here I'm going to give equation 2 and S2 and plot it from 1 second until 5 seconds. I run the code. Okay, I forgot something. I had to type hold on. So this line is not going to overwrite this line. Okay, this way, you see here, the results are so smooth. So the first part and second part are continuously connected to each other. That is because I gave the values of the first solution as the initial condition of the second part. And pay attention that the initial conditions of the second part are at 1 second, not at 0. And just to avoid these two different colors, I want to make both of the plots in the same color. So I type UI set color and I choose this blue color and I make both of the plots to be at this color. So I use a color, and I'm sorry to say it, but I have a separate video on plotting beautiful graphs in MATLAB. So if you want to find out how to change the color or line width or fonts of different parts of a plot in MATLAB, go watch the tutorial. The link is in the top right corner and also in the description. So now it is all in blue. So this was the first method. Okay. Before going on to second method, I terminate these two lines using semicolon. So method 2 is going to be numerical solution using ODE45 command. I have a separate video on how to use ODE45 command. So if you're not familiar, this is not going to be a tutorial on how to use it. So please go watch the tutorial first, then come back. So I type help ODE45 just to find the syntax, and this is going to be the syntax. So here I type this line and it asks for a function and time and initial conditions. So of course time is from 0 to 10 or maybe 0 to 5. And the initial conditions were 0 and 0 for both x and v. And how about the OD function? So I write the handle of a function named f, and I have to define this function. Function, I type dy dt is going to be equal to f of t comma y. And I have to add an n. And this is where I have to define my function. So I need to copy and paste m and c here, since this function does not have access to these variables. So I have to repeat them here. And I have to define dy dt in a state space. So I take a moment to talk about how to convert this equation into a space state representation. You know, when you are having OD45 command and you want to solve a second degree differential equation, this second degree equation has to be decomposed into two first degree equations. So I define a variable named y, and it contains two state variables, x and x dot. And I have to define y dot as these two variables, as a function of these two variables. So y dot is x dot and x double dot. So I have to write these two variables, x dot and x double dot, using only my state variables, x and x dot. So x dot is already one of the state variables, so I do not have to change it at all. But how about x double dot? I have a governing equation, and if I put cx dot in the other side of the equation and divide the whole equation by m, I find out that f minus cx dot over m is equal to x double dot. So here c and m are constants, and f is a known input to the problem, and x dot is one of my state variables. So it is an acceptable form. It is the standard form of differential equations for ODE45, and that's how I'm going to define dy dt. So it is going to be instead of x dot, I write y2. So it is the second element of y. And I type y2 semicolon fa minus c times y2, and all of them have to be divided by m. Now this is d by dt. I haven't defined fa yet, so what is fa? I know that f is a discontinuous function, so I defined it using if command. So if t is smaller or equal to 1, fa is equal to 10 newtons. Else fa is equal to 0. And let me run this code to see if I face any errors. Okay, no errors. So the solution is a variable named y with 2 columns, and the first column is position and second column is velocity. So I take x to be the first column of y and v is the second column. Now I can plot t comma x, sorry. I press F5 and you see that the blue line is the solution of dsolve command and the yellow line is the solution of OD45, and you can see that they do not match perfectly. And which one of these solutions is more correct, is more precise? Of course the dsolve command, since it is the analytical solution. And I can make the OD45 command to solve with more precision. I can add an options, and this options is going to take ODE set, and I set the relative tolerance to be 1e negative 5. So it is going to make the solution much more precise. I press F5 and now you see they perfectly match. I have to zoom a lot until they deviate from each other. Now, how can I plot the velocities? Okay, using the dsolve command, I have to take the first derivative of s. So I create a figure. I press hold on. I have plot the first derivative of s1 from 0 to 1, then from 0 to 5, no, from 1 to 5, s2. So this is the solution of dsolve command. And I can plot t comma v, and this is going to be the solution of OD45 command. If I zoom in, I can see the deviate here. And that concludes method 2. Now, method 3 is going to be a transfer function approach. So in order to find the transfer function of this equation, I have to take the Laplace transform of this equation. So this equation is in the time domain, and if you take the Laplace transform, this is the general formula of Laplace transform, and I'm not going to go into the details of that. I suppose you know how to do it. There are many books out there, control theory books and vibration books, to do that. But this is the Laplace transform of this equation, but with the assumption that the initial conditions are 0. So the transfer function approach, by definition, always has 0 initial conditions. This is a shortcoming of this method, but for our current example, luckily the mass is initially at rest, so we can use this approach. So I take the Laplace transform, and now x and f are a function of s, which is the Laplace variable. It is an imaginary number. So I factor out x from these two terms, and x over f is going to be equal to 1 over ms squared plus cs. So ms squared plus cs is going to go in the denominator in the other side, and f is going to go in the denominator of the left side. And what this means is a relationship between the output to the input. So f is the input of our problem, but x is the output, is the desired output, what we are looking for, what we want to find out what it is. So this is the transfer function. And if I type help tf is the transfer function creating command in MATLAB. And this is the syntax. It takes the numerator and denominator. So the numerator is 1, and the denominator has to be defined in polynomial approach. I have a separate video on how to work with polynomials in MATLAB. If you want to find out more about this capability, go watch the tutorial and come back. So the way to define this polynomial using an array is by typing MC0. So MATLAB looks at this as a second degree polynomial, mx squared plus cx plus 0. And this is our transfer function. And in order to solve the response of this transfer function to our force, I have to use a function named lsim. And this function computes the time response simulation of a dynamic system to arbitrary input. So our input is arbitrary, it is not continuous, it is not a known function, and I have to define it in this way. So I copy and paste the syntax. It knows the sys already. It needs u, and u is, as defined here, the input signal, and t has to be time sample. So t is going to be linear space of 0 until 5 seconds in 501 points. Okay. And how about u? And for u, from the first until 101, it is equal to 10 newtons. And for u from 102 all the way to 501, it is equal to 0. I terminate it and press F5 to see if I see any errors. No, I did not see any errors. And maybe now I can plot t comma y. Okay, now here the purple line is the response of the system using transfer function approach. You can see that it is not exactly the result we got from dsolve and OD45, but it is good enough for us. And this was method 3. Let's go on to method 4. State space representation. And I want to take a moment and talk about how to define this differential equation as a state space representation. So again, as in the OD45 solution, I have to select 2 state variables. And y2, since my differential equation is second order. And I take x and x dot to be my state variables. And what I have to do is I have to define an equation y dot equal to a times my state variables plus b times u. And u is going to be the input of my problem. So generally, this input can be a vector. My system can have 10 different inputs. Our system only has one input, which is the external force, but it could be a vector with multiple inputs. But for now, it is not going to be a vector. It is only an external force. So u is going to be fa. And I have to define y dot as a linear combination of my state variables and my input function. So y dot is equal to a times x plus b times f. And how can I write this equation in this form? Okay, I repeat this line and I say y dot is x dot and x double dot. Again, x dot, you do not have to change it, but x double dot has to be written in this form. And I take out fa from this matrix and add it into a separate matrix. So x dot is unchanged, it is summed by 0, and negative cx dot over m plus fa over m. And this is a form that can be converted into a state space representation. So don't forget what we're going to do. We wanted to write y dot in this form: a matrix times my state variables plus a matrix times my input. And what we did here was I wrote the first term as 0 and 1. So this line, this first row is going to be multiplied by its column, and 0 times x plus 1 times x dot is going to be x dot, and 0 times x plus negative c over m times x dot is this value. And the same goes here. 0 times f is 0, and 1 over m times f is f over m. So here I have created the matrix A and the matrix B, and that's what I need to do. So if I type help ss, you can see to define a state space variable, it asks for such syntax. It asks for A, B, C, and D. So I copy and paste it here. I terminate it, and what was A? It is this matrix, 0, 1, then 0, negative C over M. This is A. How about B? It was 0 and 1 over M. Okay. Next, I have to find C and D. And C and D define my output. What is my desired output? What is the variable that I'm looking for? I want to find out. It can be any linear combination of x and x dot and f. So I wrote 3 different outputs here. So this one only gives me the position. It only gives me x. So 0 multiplied by f is 0, and 1 times x is x, and 0 times x dot is 0. So this form only gives me x. But if I write this matrix as 0 and 1, it only gives me x dot. And if I write it as a unity matrix, 1, 0, 0, 1, it gives me both x and x dot. Of course, maybe I made a mistake here. If I want to write it here, this D matrix has to be 0 and 0. It needs to have 2 elements. But what I'm going to do now is I only look for x. So I define C as 1 and 0 and D as 0. Now I have defined A, B, C, and D. Even if D is equal to 0, you have to define it. You cannot forget it at all. And the others is the same as method 3. So lsim function takes a system. This system can be defined as a transfer function or a state space representation. No difference. There is a difference that if you use a state space approach, you can add the initial conditions. This is the difference. But with transfer function method, you cannot add an initial condition. So I run, and this green line is the state space approach. Okay, here I only run this part using Control Enter, and you can see here, this is the response from state space approach. Or I can ask for both position and velocity. So I go for this line, and just remember that FA has to be multiplied by 2 elements, 0 and 0, as I did it here. I run it, and let me only run this method 4. Here is the response of the system using state space representation. And that concludes method 4. And for method 5, I have to go to Simulink. To find the answer of this differential equation in Simulink, I go back to the initial equation, and instead of x double dot, I write acceleration, and instead of x dot, I write velocity. And I convert this form into this form. So A is f minus cv over m, and this is what I'm going to create in Simulink. So when you have second order differential equations, you need two integrators. So this is velocity, and if you integrate it, you come up with position. And this is acceleration. You know, the integration of acceleration is velocity, and the integration of velocity is position. If you have any initial condition, you can add it here, but my equation is having no initial conditions. They are 0, so I don't need to change anything. I have a separate video on how to solve differential equations using Simulink, so you may want to check that tutorial too. I add a scope command to see the solution of position, and also I can add a scope command for velocity. Now acceleration is f minus cv over m. So I need a summation block, and what it is going to do, it is going to sum f over m and negative c over m. So negative c I convert it into a minus, and the velocity has to be multiplied by c and be fed into here. So I need again, the velocity has to be multiplied by c and divided by m. So the gain is c over m. I press Ctrl I, and the velocity is multiplied by c over m, and with a negative sign, it is going to be summed by the force, and the force is step command. So up until 1 second, it is equal to 10 newtons. Then it is 0. I don't forget that it has to be divided by m, so I multiply it by 1 over m. I can run it now, but just to show you how to add constants in Simulink, I clean the workspace. Now if I run, I see an error. It does not know what is M and what is C. In order to do that, I go to the Modeling tab here. I go to Model Explorer, and in the Model workspace, I add two variables named C and M. C is 0.3 and M is 0.5. Now I have defined these two constants, and now I can run the model. So here, this is the position and this is velocity for 10 seconds. Now I go to method 5, or no, method 6, and it is the transfer function approach in Simulink. And defining transfer function in Simulink is the same as in MATLAB. The numerator was 1 and the denominator is MC0. I make it bigger to see the equation, ms double dot plus cs. So in this way, MATLAB shows you what is your transfer function. I make a copy of my input force, and I make a copy of a scope command. Now I run, and here is the result. You see, how easy it is to use transfer function approach in Simulink. Next, I go to a state space. This is method number 7. And again, I have a copy of my input force and a scope to display the results. And A, B, C, and D have to be defined the same way as we did them before. So D was 0 and 0. I go back to C them. C was 1, 0, 0, 1. So 1, 0, 0, 1. How about A and B? So this was A and this is B. So B is 0 and 1 over M. And A is 0, 1, semicolon, 0, negative C over M. Okay. Now I run and I can see both velocity and position. And the last method, the 8th method, is using Simscape. So I go to library browser, I find Simscape. Under foundation library, I find mechanical. And I need translational elements, mass, a mechanical translational reference, and a translational damper. I also need, from mechanical sources, an ideal force. Also, I need a translational motion sensor. So I press Ctrl I, I connect the C port to my reference. I connect the mass to the damper. I double click on the mass and set it to 0.5 kilograms with 2 ports. I convert the ideal force here. You know, I have talked about all of these elements previously in my vibration course, so you may want to check those tutorials too. I set the translational damper to be 0.3 Newton second per meter. I need a solver configuration block. What else do I need? I need 2 PS Simulink converters, one for velocity, one for position. And I need 2 scope commands. Or maybe I can draw both of them in a single plot. I need a copy of my translational reference to connect it to this force, and I define the force as a physical signal step. So at 1 second it goes from 10 to 0 newtons. Let me run it. And here I can see this is the same result. In all of the results, the velocity at 1 second was almost equal to 15, as you can see in any of these plots. Okay, not this one. Here it is almost equal to 15, and if I press F5 here you can see velocity is almost 15. And that concludes this tutorial. Thank you for watching. I hope you enjoyed it, and bye bye.